those, okay, I think the video isn't working, but being those quite interesting movements of the colors, we can immediately think on something magical behind there, or giving the droplets some human abilities like seeing or feeling each other. But in fact, there is no magic behind this, but it's only physical laws. So this is what my task is about. Droplets having different concentrations of food coloring containing propylene glycol, moving beautiful and intricate patterns when placed on a clear glass slide. A wide variety of autonomous fluidic machines can be produced using this property. Implement diverse arithmetic operations using such droplets and optimize the operation speed. So due to this task, we already see a nice structure of our problem, how we can tackle it. First of all, we need to understand the phenomenon and reproduce it. The second thing is that we have to establish some mathematical models, and the third thing to increase our operation speed. So first of all, I already said there's no magic behind. So what is our phenomenon based on? It's based on the mixture of water and propylene glycol. As we put only a droplet of water or only propylene glycol on a glass slide, it will spread entirely. But if you have a mixture, we have a nice droplet. So this is due to the lower surface tension of our propylene glycol and the lower vapor pressure. So when we look more carefully on one droplet, we see that on the edges of the droplet we have a higher evaporation as we have a higher surface to volume area, and that's why we get a higher concentration of water in the center. This leads finally to a Marangoni stress, what makes having this stable angle theta. When we look a bit closer, we see in this photo, that should be real but it's not working, I'm sorry, we see that there is a movement towards the center of the droplets on the top and a movement back on the downside, but the movement, the counterflow, is quite much slower. So as I said, the most important thing is that we have this stable angular theta. So what happens if we put more than only one droplet on one glass slide? We see we have to distinguish between long-range and short-range interaction. If we have a long-range interaction, we have here different vapor. You might see the second droplet that is right here.
No.
Okay, so I'm sorry. So here should be another droplet. So you see, normally there are two droplets, and they build another vapor droplet from around each other. That's like the vapor profile of the both. They are crossing in this area. So we have a cross in here. That's why we have the highest relative humidity in this area. That's why we don't have a high evaporation rate, what leads finally to push towards each other. So they are moving towards each other with an increasing speed depending on the decreasing distance. With a short-range interaction, we see that when we have two droplets of the same propylene glycol content, they will merge. But if we have two droplets that have different propylene glycol concentration, as we see here, they will start to change each other. That's due to the fact that as soon as we have a physical contact between, they are exchanging fluids, and that's why we can get an asymmetry, what leads to this chasing effect. So what do we need to reproduce all these phenomena? First of all, we need food color based on propylene glycol. The second thing, we need the permanent therapy marker. And the third thing is our class slide. Our class slide is very important. We can use different kinds of class slide, but the most important fact is that the spreading parameter of this class slide is bigger than 0 because we need a high energy class slide. I also mentioned the relative humidity often in my explanation, so it's quite important to have a relative humidity that is not too high because otherwise our effect wouldn't occur. So we conducted some experiments with different class slides, also with different food coloring, and found out that for us the corona discharge class slide is the best one. But the task says not only to make these movements, but to find diverse arithmetic operations. So what thoughts do we have about this? I want to introduce two thoughts for you before going to the third thought that we finally used. So at first we thought about a number line. So we can use a number line to add and subtract. So we use our chasing effect of two droplets to add and subtract numbers. If we calibrate the whole system, we can find out, due to different concentrations and different volumes, we can determine how long is the distance they will travel before the effect is away. So that's why we can calibrate it. Another effect that's quite interesting is that when we have a too high concentration difference, we have a repulsive force and not the chasing force anymore, and we also have an explanation to this. So the second device was a multiplicator. So we divided the two factors in volume and color factor. We started with a special amount of droplets with a defined volume, and we can analyze finally our end droplets. So we have the same propylene glycol content in the starting droplet, so when they are merging, we can analyze this one. By analyzing this, we find out the volume, we find our first factor, and also we can use the hex color parameter by analyzing photos, and that's why we can find out our final calculation. But as you see, these calculations are not really big and also not really fast. So what can we do to increase our operation speed? We divided this section into two different parts. First of all, the kind of method, and the second one, the droplet movement itself. Regarding the kind of method, we started to calculate with logical operators. So using logical operators, as you all know, you can make the same as adding and multiplicating, and you can basically calculate everything that you want. So we introduced those 4 logical operators, and here you can see the equivalents for these operators in our droplet movements. Using them, we could combine it to a basic calculator, but this calculator can only calculate up to 2. So it's not really a lot that we calculate, but it's fine that it's already working. So what can we do to establish a bit more complex calculations? We derive this table so that we need some input, so we need x, y, and also an input from the further logical operator that comes out. Using this, we can derive our logical equations, and you see already in those logical equations we have 12 different gates that we need, 12 different logical gates. When we combine them, we can build our summing amplifier. That is the basis for all our following calculations. Using the summing amplifier, for example, we can symbolize it in this, and when we use this, for example, we can calculate 13 plus 5, but that's only one example. So I also told about speeding up the droplet interaction itself. So for finding out what are the most important parameters on this, we first of all need to derive our theory. So we need to derive the distance of the 2 droplets, as well as the relative humidity and the angle depending on this relative humidity, as well as the surface tension. And having this, we can find out about our net force, and with our net force we finally can calculate our speed, our velocity. And of course our velocity, this is exactly what we want to improve. So looking on those parameters and also on our experiment, we can find out the most important parameters. These are the distance, the relative humidity, the surface, the concentration difference, the volume and the volume difference, as well as the acclivity of our operation area and the additional energy, for example, when heating our whole device. First of all, it's quite important that these parameters interact, because, for example, we always have to find a good mean value for those, because when we want to speed up our movements, we have to increase the evaporation rate. But when we increase our evaporation rate, our effect will be away more quickly, so we always have to find a middle mean. Also, for example, when increasing our volume, we affect also our distance, so they will get into short-range interaction more quickly. So when trying out all of these different parameters due to our gates, we can finally find out the best parameters and the best conditions, and using them we can find out what improvement we have by improving our parameters, and finally find out our new velocity, our improved velocity. Calculating the rate between them, we have an improvement of 5% on our first calculator and of 7% on our second calculator. So let's come to a conclusion. First of all, we could reproduce our droplet movements, or at least some of the droplet movements. Second part, we developed a theoretical approach that we finally could use also to speed up our whole system. We could develop different mathematical operation systems, and we had an approach to investigate the parameters, could improve our method, and had good accordance of the theory and our experiment. So, of course, we also have further ideas. For example, we want to use the different probabilities of our droplet, for example, the different kinds of colors, the different concentrations, not only to say in the logical gates we have like a 1 or a 0 so that we can calculate, but we also want to use logic to increase our speed by using different kinds, not only 1 and 0, but different kinds of measurements. Also, we can with our logical gates, we can build up a storage, like a flip-flop storage that we can use. So these are just ideas that we haven't tackled yet, but we would like to tackle. So I think I'm looking forward to the discussion now.
Okay. Good morning, ladies and gentlemen. My name is Paweł Szczupkowski. I represent the team of Poland from University of Warsaw. I wear these glasses not to look smart, but just to look proper, to see proper. And about your presentation, I really appreciate your presentation. You included lots of data. You also were well prepared for your presentation. You have presented the idea of calculator, which was the core of our issue that we had to solve. You had great prepared theory that I would like to discuss later, because I think there is need to spend more time over the theory of such a problem. Okay, it works already. Also, you've measured a lot of parameters, which was great, and give us some optimization details and what you want to do in the future. I would also like to focus on that, because I'm pretty interested. How do you want to do a flip-flop, and is it be working in that way that you would show us? The next things that I observed was lack of the quantitative dependencies. Like, you've got that equation, but really you didn't mention anything about this. You somehow didn't say about your measurement confirming that theory. So maybe we would have to discuss it. And also, I didn't heard anything about the time. Like, our calculator would do the addition thing, for example, add 5 to 5 in, for example, 1 hour. Okay, that would be great, and would totally confirm your presentation for all. Also, the experimental validation and agreement with theory, this is what I was talking about. And I'm not sure if you had some measurements and so on, but I think we'll go to this later. And to conclude this presentation, if it sticks to the problem content, I think you've done a great job, because you did everything that's written here. You think about optimization speed. Maybe you implement this diverse arithmetic operation, because I didn't see how it exactly worked in the experiment. There was no video at all, and so on. Yes, you just fulfilled this problem, not with everything, but we'll discuss it later, I hope. And I would have also some questions. For example, what are the error rates? Because the gates can also have some error rate, and how do you approximate this error rate, and if you checked that, and so on and so forth. Also, what's the speed of this calculation? This is really important for us, because we would like to optimize our device to be quicker than our minds, I guess. And also, what kind of operation you are able to do. If you can enlarge this addition of number 5 to number 5, to, for example, adding 194 to 160, and so on. Okay, so I think these are the good questions that you will need to answer in a minute, and hope maybe you could just plug in your computer and jump into some slides.
Okay, yes. So you want to change?
Yes, okay. That's right. Thank you.
5 minutes for discussion.
Maybe one of my team members will do it. You can already ask questions. I think that's more.
Yes, yes. So maybe Could you move on to the slide? I guess, I don't remember, it was about 32 or something. This with an equations, like derivative of x by the time. That was the slide.
Rated on the theoretical or on the mathematical?
Oh, this one, 36 that was. And
Who's back?
36.
Which one?
36, the next.
I think there is one that is just erased. Maybe before? I think you mean this one?
Yes, this one. Oh, sorry.
Sorry.
So, what are these things all about? What is C drag? What are gammas? And for what purpose is this integral here?
Okay, so first of all, I think that I explained some of the variables already here. C drag I can directly say because we have this net force. But this net force, of course, it's balanced by the drag force. If you have the drag force, you have to take this into account. I can show you how we get to this equation if you want. So we can.
How long did it take? Because I don't think.
Maybe we can just start, and then if you think it's too long, so we just stop. So when you see here. So first of all, the whole equation is based on our evaporation profile.
Okay.
So we use first of all a heat equation. Then
and sorry to interrupt you. Maybe do you know how does the heat influences the whole thing that occurs?
Yes. So this is only just on basically our mainly our mean temperature in rooms. But as I pointed out on my other slide. I had some parameters, and you see the additional energy on the end. That was like when you heat it or when you give additional energy to it. So when you heat the glass slide, for example. Heating the glass slide, of course, leads to a higher evaporation rate. That means, again, that the water, because the water evaporates 100 times more quickly than a propylene glycol, the water, maybe I just finish this, because the water will evaporate more quickly, so you have the higher effect. So the droplet is moving faster, but not as long. You know, because the evaporation.
Yes. And what about this effect at the in the really near side when you meet the two droplets?
So what the short range interaction.
Yes, the short range. What they do then if we give the temperature higher?
If you have the temperature higher.
Yes, will they mix or will they run?
Yes, they will, exactly, they will mix more quickly. So in general they mix when they have the same propylene glycol content. As the water is evaporating, and if you heat
but I mean you've got other glycol contains into droplets, and you increase the temperature.
Yes. Okay. I think I understand. You increase the temperature. That's
why. Will they mix?
Yes, they will mix because they will mix even if you don't increase the temperature. But if you increase the temperature, they will mix more quickly because the evaporation rate is higher. So the water evaporates more quickly, so that they get the same propylene glycol content.
The question is, in higher temperatures, will you observe this effect that one droplet is running from the other?
Yes, but only really short distance and really a short time.
Thanks a lot. So maybe let's move on to the measurements. Could you please prove what you've done here, this whole theory with any measurements? Have you got some videos?
You mean the arithmetic evaporations, or you mean this theory?
Evaporation.
So from our arithmetic measurements.
Yes, the dependence that you derived, how the force is connected to the temperature and the radius.
So you mean in this final equation?
Yes.
Okay, these equations we use to calculate our theoretical droplet movements.
So you didn't do any experiments at all?
We did experiments, as I showed you on the further slide. If I may change it on. So we were originally.
Okay, I guess.
Okay, so I'm going to report the review, the Fluidic Calculator presentation from the German team. So the slides don't work. Okay, I'm going to do them by oral, but So the problem is that having different the statement was that to understand the problem, implement diverse arithmetic operations using such droplets and optimize the operation speed. Okay, so for the summary of the report and the opposition, so for the reporter, we had an understanding of the problem. There were no presentation of the experiments. From the theoretical point of view, we had theory of Marangoni stress and the different ways to compute calculation. For the opponent, there was a summary of the presentation, and he highlighted the lack of experiments from the reporter. For the reporter, you had a good theoretical analysis, but I would like you to cite the source of the theory because it's well known and it's in a single article that is really well known. So we didn't have that. You didn't explain the Marangoni stress; you just mentioned it. There was no clear explanation of the chasing and the merging. We didn't have any. We had an unclear experimental setup for the sum. No incertitudes. The multiplication, we didn't know how you implemented the color scale. For the experimental difficulty of the computation, because it's quite difficult. And you said a good accordance of theory with experiments. I'm sorry, I didn't see any experiments. So for the reviewing the opponent now, so you had a good summary of the presentation. You highlighted the fact that she had a good theoretical understanding of the problem, but you have also highlighted the lack of experiments. But actually, you went on to the for negative points. You went on to the discussing the big force of attraction. But I would like you to stay on the physics and on the ability to compute these things. So now to compute two points to discuss that I would like to discuss. It's very quickly, is the setup doable? We didn't say anything about this. There is some problem with the surface, the heat, the pressure, the size, the concentration of the droplets, and I want us to go back to this physics. Also, what is the most important parameter of the problem? The binary adder, how do you do the parallel computation, which is really hard in this problem? And the physics of continuous current in your transistors. So I'd like to invite you to discuss now. And I want you the opponent, to highlight to me what experiments are doable and is the setup doable.
Yes, thank you for this time, because now finally we have this time to discuss further. Did you, this is the question to the reporter, did you actually make a gate?
I'm sorry, I just want,
No.
Is it doable for you? Like, can you do it?
Yes,
Do you think it's possible to do it?
Of course.
Everything she said?
Flip-flop is not doable.
Okay. What do you think about this?
Yes, first of all, as I said, we implemented in the praxis only the first gate calculating to 2. And the last gate, the bigger one, I mentioned it, we didn't put into theory, but we in praxis. But we think that it is doable.
So which gate did you calculate? Can you explain to us?
Yes, we measured the first one that when you have this impact, x, y, and you have the result. This one, where we have only calculated until 2.
Okay, so may I ask, how does this experimental setup, how does this gate look like?
I can show you.
Or maybe it would be easier
Maybe it would be easier to draw. Yeah, it's maybe easier to draw. Can you just draw it on the board,
Can you
please?
change the slides? I think it's quite important that first of all explaining with the single parts of the...
Let's just draw the experimental setup, the
Okay.
scheme.
Yes, so we see that when we have, for example, an x and OR operator, we have to think about how can we implement it. So when we have a droplet here, flowing down here, then this droplet will continue here. But, sorry. Yeah, maybe, but I think I need the slide to make it more clearly.
No, come on, go ahead.
Okay, then
I think
maybe,
you can
yes.
do it.
Can you just
Because
go
the- or
back, down,
can-
down,
can-
down,
can
down,
you
down to
maybe-
the single gates? Because I think that's quite important. This one before, this one, please, 21? Yes. 21, can you maybe pull it on?
Wait, could you
Yes,
do it
and
on
now
the
click
board?
1 times.
Okay,
Why don't you answer, please?
Okay, so when we have put in a droplet here, with the same concentration, you see, it will merge here, and there's no continuous flow. If you put in here a droplet of a different concentration, it will chase the droplet and the thing will go on. So this is the first operator.
But
We
why
have
the droplets should move? Why the singular droplets should move?
The single droplet move to an intrinsic, as I said, we have an equality here. That's what I pointed out in my last slide of the parameters.
Yes, so what are the
that's why-
sizes of the gates here? Is there in centimeters or in millimeters or what? What are the sizes of these
These
gates?
approximately from here to here,
Mm-hmm.
this is 1.7 centimeters.
Okay, and is there any attraction for 1.7 centimeter?
What attraction?
Attraction with these two droplets.
From
Can they
this
move?
range,
Yes.
yes, there is attraction.
Okay.
Okay, so
I can also explain the other one.
let's
For
look at
example-
parallel computation. Okay, you talked about big computation. Like, how do you implement parallel
Fine.
computation?
Okay. So
No.
Do you have any idea
sorry,
about
sorry,
how
but
to
I think there is one
Please,
misunderstanding.
let him please
Okay.
answer this question. Do you think like it's possible to implement the parallel computation she talked about in the?
the exact one that the reporter was talking about, I think it's non-doable.
So what do you think is doable actually?
Actually, there might be other ways to do it, but I guess we don't have the time to discuss it.
Maybe just present us a bit. We have some time. Like, what is the simplest computation you think is really doable in the experiment?
You can just divide it into the two containers and watch on which container
Yes.
there would be the
We
other.
really wonder, because this is a nice experimental setup, and we had some like. We think
I'm sorry. What experimental setup? Can you elaborate, please?
That's the thing that they thought about the experiment, how to set up, but they didn't actually make it, and we wonder what would be the error rate of your experimental setup if you would do this experimental
The
setup.
computations, error rate of the computation, can you approximate it anyhow?
At least I
The-
have formulate equations if you don't have measurements, something like this, because it's really important. Because, like,
Yes. So first of all, as I said, we just focus on the increase of our speed. So that's why we focus on this part and not on the error rate of our system.
But
Okay.
So we try to, in total and the mean value,
Yes.
we try to increase our speed.
Right, so you
Yes.
try to increase your speed so that in the theoretical logical circuits you build, it's faster, right?
Yes,
But
7%.
in most of
that
your
we
complex
have.
circuits, you have parallel entries, like parallel
No,
current. And
No,
this is
there's no current.
non-dual.
There are no transistors. There are no currents.
You have logical inputs that arrive, like two logical inputs arriving at the same
But
gate.
they are all liquid.
Alright, and that's what makes it impossible without great timing. If you want to have two inputs coming at the same time, they need to come at the same time, so you have to control the flow of those bubbles, of those droplets, so that they arrive at the
Yes.
gate. How do you do that?
We control them with the different concentration rate as well as, for example, the other parameters like a fluidity here.
Concretely,
If
how
we
do you do
have-
that?
Yes, for example, if we have a higher angle here, of course they will be quicker. If we
Alright,
have a lower angle, if you put heat on it, they will be quicker. But
your calculator does not depend on the droplets you put in it, right? And the speed of the droplets depends on the concentration in propylene
Sorry,
glycol. Right, so the speed of the droplets
Yes.
depends on the size and the concentration in
and on the
propylene glycol,
concentration,
right?
on the different relative humidity
Exactly.
around it,
But your
on the
angle
different...
does not take that into account. So for different droplets, you'll have different speeds, and they arrive at different times in your gates.
Yes, so that's why we can change the different the different ways, the different paths that they take. So for example, we can make one path where the droplet is quicker, we can make a bit larger than the other
Exactly. So
path.
what you
We can
said-
use
yeah.
Okay, I think we understand
Okay,
that. We understand that this is really a complicated thing. So I just want to ask one question to the opponent right now. What do you think is the most important parameter in the problem that will help us to enhance the quality of our calculations?
Excuse me.
Can the most important parameter to get the best results we can get? Like what is the experiment we're really sensible on?
What we have to check. I guess we have to check the time on which this both droplet would merge. This is the really important parameters, and also I would like to ask, what is the time over which the two droplets in this NOT gate will merge over this 0.7 centimeters.
They have the highest speed that we had was 3 millimeters per second, and in mean values it was 2 millimeters per second.
2 millimeters
The
per second.
velocity. Yes.
So they will merge after the 2 seconds. More over 2 seconds.
When you have
yes?
2 yeah, in this case you have more than 3.
Sorry.
2 millimeters
Yes,
per minute, I'm sorry, not per second, per minute.
Yeah. Okay.
Sorry, 2 millimeters per minute, and 3 was the highest.
So about 3 minutes.
Yes, but maybe going to your point, I think the most important parameter is the relative humidity, where it's really crucial, because if you have too high relative humidity, the whole effect won't happen.
And so, did you
this
do
will
any
change
measurement
the
on the
whole-
importance of the
On the relative humidity?
Yes, exactly.
I'm sorry.
Can you just answer the question, please?
Yes, we have, yes.
I'm sorry.
We were
Can
at
you
the
do it on the
Institute of
board?
Erlangen, that we had help from a
Yes, she may talk if she wants right now. We have no problem with everybody participating. I just want a quick answer about the humidity problem.
Okay, yes,
Yes. So what results did you get for the humidity?
for the humidity.
Yes.
So when we have a high relative humidity, our contact angle is quite high because the spreading is higher. So we don't have a step. So you see, this one, it's more like when you have about maybe 40%, like in our room at the moment. If you have maybe 16, 7%, it's getting a bit like
Can
this.
you give us a value of the best
Finally,
humidity
yes.
to get the
Best
experiment
we
going?
had 45% relative humidity.
Why?
For that.
Can I ask why?
This was because we used room humidity because we didn't have the possibility to take it into a chamber where we controlled really exactly the relative humidity, only for the measurements. Then we could control it precisely. But for our experiments, we had room humidity.
All right, thank you for your discussion. Now let's move on to the conclusion by the reporter, please.
Okay, so first of all, thanks a lot for the discussion between the opponent, the reviewer. And I think what's quite important that you raised the point that we don't have as many experimental data sets, what's quite right, because we focused on other parts. Also, I think it was quite interesting to discuss about the different way how the gates work, because I just had not enough time to enlarge this in the presentation of 10 minutes only. I also like that some of the audience participated, put in some interesting ideas, and we could discuss about this. And yes, I think I liked the discussion, and thank you.
Thank you. And now it's time for more questions from the jury members. I see we have at least two. Okay.
So both to the reporter and the opponent, how many operations do you think you can implement in a calculator like this? How many different arithmetic operations? So addition and
One.
You mean from addition, subtraction, multiplication, and with one setup, or with several setups?
It's possible.
One setup.
It's only possible
One
to do
setup.
one.
No.
It's possible to do.
what do you think?
You can have the addition and the multiplication, because if you use the binary numbers, it's
I would
quite the same, but changing just
Okay.
the results.
I would also depend on the logical gates, because with the logical gates, like the AND operator, it's approximately the same as the multiplication. The OR operator, it's approximately the same as the addition, and so you can implement it with those.
Okay, so two, right?
Yes.
Thanks.
Two.
So, when I have it,
Yeah, please.
to the reporter question, have you team members telephone with photo or video cameras? Yes,
Of the-
of course.
Yes.
Huh? Where is the video of your experiments? No one.
Yes.
Show, please.
Okay.
No one.
Yeah. They're
Yes.
just on the.
You cannot prove that you make.
Please stick to the questions.
Question, да. Camera S.
We got the reply. There are
Cameras
none.
exist.
There are none
No.
at the moment.
We know, cameras exist.
There are none shown for now. Okay. Next question, please.
Small question. I still do not understand how you, it's a statement of course, how you implement this logical operation. For example, just
You will
very,
have time for remarks later.
it's not, and now I have a question.
Okay.
How, very shortly, how do you implement not operation?
Not operation.
Yes.
Not, let's, for example, this one. So you can put in, for example, like a 1 or a 0. When you put in a droplet of the same concentration, they will merge. and you won't have any output there.
One droplet. I don't understand where the second droplet came from.
This droplet.
Could you draw it very shortly?
Yes. This one is just we prepare it. We prepare this one. We have prepared this droplet. When you put in a droplet of the same concentration, they will merge, and you won't have an output. We put in a droplet of a different concentration, they will chase each other. The same, for example, when you have this operation, the AND operation, when you have a droplet from this and from this, they will merge and they will continue in this way.
It doesn't have binary outcome, it's something more complicated. Okay, I understood. Thank you.
That's okay. Another question, please.
Why droplets with the same concentration join and why droplets with different concentration reject?
No, with different concentration, they just chase each other. They don't reject. If you have a too high concentration difference, that's right, they will repulse each other. And this is due to, then we have a high propylene glycol concentration. And all the theory is based on a high water concentration. So if we have a high water concentration, it's right that they start like this, chasing each other in this direction.
Yes, but why?
If we have
Why?
Okay, here.
Explain how. Physics. The physics would
Yes.
be lower.
Okay, so we have here, as soon as they merge each other, as soon as they get into physical contact, they exchange fluids, they exchange liquids. When we have an exchange of the liquids in this area, we get a different evaporation rate. And if we have a higher evaporation rate, we have a higher rate, less concentration of water. Because in the region where we don't have a high evaporation rate, we have more water. Because the water evaporates 100 times more quickly than the propylene glycol. And this is the effect. So you can do it not only with propylene glycol and water, you can also do it with different liquids. The most important thing is that the surface tension is high and also our evaporation rate. So they are less volatile.
Maybe I can answer shortly this question. The mixing enthalpy for the droplets with the same concentration would be 0, so the summarized energy that the droplet would have after merging is higher, so it's energetically better for droplet to join when having the same concentration.
When having the same, but not when having
Yes.
a different concentration.
That's right.
All right, we have time for more questions. Yes, we have.
How well do each of you think that this question was answered? Just
Which question?
The whole
the
problem.
question, the whole
the problem. Okay.
I think I have to be nice, but I think it's quite bad actually, because the experiment is so hard. Like to do just one transistor, just one.
There's no
zero.
transistor
Please,
at all.
let me answer. Please. Let me answer. Just one transistor. You have to really optimize the shape, and optimizing the shape is not trivial. Like saying you have two things coming together and they merge. It's really a fine-tuned process, and it's really complicated. So I think this is not possible.
what do you think?
Yeah, my opinion is also quite the same, because after the presentation I thought it was really great, but after the discussion we find out that you really did not make so many measurements to prove what you think about it. Even though you say about this problem and so on, you didn't fulfill this.
We proved that it works, but we just did not make enough measurements to make reasonable plots about this. Because it's not enough if you just make plots with an error bar of this. Yeah, we proved that it works, but not that
you
it's...
can answer the question yourself.
Yep.
It was a
Yes.
question for everyone. So answer
Okay,
yourself.
okay. So I think that we just fulfilled the 3 different parts of the task. We also could optimize our operation speed, but of course only on a single scale and not on the too complex operation method, as we were running out of time. But as we have more measurements again, we could of course have more plots. But it's not, as you saw, there are so many parameters, there are so many influential factors. We made measurements on all of those, but we could not make 100 measurements of all of the different parameters, changing them. So it's not really reasonable to make plots with maybe 5 measurements that we put of all the single parameters.
All right, thank you.
I think there are
for-
some limits also. You need
Oh,
maybe
yeah.
10 years to investigate the whole problem of all the parameters.
All right, that's it. We don't have time for the questions. You'll have time for the remarks afterwards, and you'll have all the time after.